Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy here at Foothill College in Los Altos Hills, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on YouTube or hearing us on your local podcast channel. This is the Silicon Valley Astronomy Lecture Series, which for 25 years has brought introductory astronomy discussions with noted astronomers to people all around Silicon Valley and the world. We are co-sponsored by the Foothill College Science, Technology, Engineering, and Mathematics Division, by the SETI, or the Search for Extraterrestrial Intelligence Institute, which is in Mountain View, and the Venerable Astronomical Society of the Pacific in San Francisco. All three organizations are in the business of astronomy outreach, and that's what we hope to do with these lectures. If you are watching us on YouTube and want to be notified as new lectures become available, I want to encourage you to subscribe to this channel and also to click on the bell, because YouTube is now very finicky about whom they notify, and you have to click on that bell symbol to be in the inner parts of the mailing list and actually get notified. So with that, let me now introduce our speaker tonight, discussing work about the James Webb Space Telescope and what it can do with planets orbiting other stars. Our speaker is Dr. Jonathan Fortney. He is the Department Chair of Astronomy and Astrophysics at the University of California, Santa Cruz. He's a planetary astrophysicist who works to understand what planets and their atmospheres are made of, both for exoplanets around other stars and for the planets with which we share our solar system. He has been a member of the science teams for a number of NASA space missions, like the Cassini mission to Saturn and the Kepler mission, which found over 3,000 exoplanets. But now he's working with the James Webb Space Telescope, 1 million miles from Earth, and his talk tonight will be New Worlds, analyzing the atmospheres of exoplanets with the James Webb Space Telescope. It's a privilege for me to introduce Dr. Jonathan Fortney.
It's great to be here. Everyone hear me okay? All right. Thank you for the very nice introduction, Andrew, and thanks for the invitation to be here. So I'm a professor at UC Santa Cruz. I also run this thing called the Other Worlds Laboratory. That's a summer visitor program. We bring scientists from all over the world who are studying exoplanets to the Santa Cruz campus for a workshop to generate new ideas and new collaborations in exoplanet science. I'm also on Twitter and Blue Sky, or X and Blue Sky, for those who are so inclined. So tonight I'll be talking to you about both exoplanets, how we try to study their atmospheres, and also how the James Webb Space Telescope helps us do that, and some of the particular aspects of it that make it so nice for studying exoplanets. So the first part, I'll be talking about sort of different wavelengths of light. James Webb works in the infrared, then I'll talk about the Webb telescope, and then I'll move on to talking about exoplanets. First, talking more about gas giant planets like Jupiter and Saturn, exoplanet versions of those, and then at the end talking more about terrestrial planets and what we're trying to do to understand them as well. So this is a painting of Isaac Newton, 1672, and he famously broke light up into its component colors. White light is a combination of, just like a rainbow, red to violet. But that is just one part of the spectrum, of course. It's a thin amount of light that we can see. There's wavelengths that we can't see at much longer wavelengths and at much shorter wavelengths. And so, of course, we can see visible light, but wavelengths just shorter than we can see are the ultraviolet and then X-ray and gamma ray. At wavelengths just longer than red light that we also can't see, we have the near-infrared, mid-infrared, microwave, and radio. And so all of these wavelengths of light are sort of buzzing around our lives all the time. We just happen to have really great detectors in our heads that can detect a very narrow wavelength range, our eyeballs. But the universe is emitting all of these wavelengths, and as modern astronomers, we need to build instruments that are able to do this. And this is really the history of the 20th century of astronomy till the 21st century, is really recognizing the universe is operating in all of these wavelengths, and we need to be able to build detectors that can sense these different wavelengths. And so we have that in our modern astronomy today. So visible light, Hubble Space Telescope mostly works in the visible and the ultraviolet and a little bit of infrared, but around the visible. But we have telescopes up in space that can see X-rays, gamma rays. We have telescopes both in space and from the ground that can do microwaves, radio waves. The VLA is a famous one down in New Mexico. I visited there once as a tourist back when I was a grad student 25 years ago. And so James Webb Space Telescope sits here in the infrared, sort of wavelengths about 10 times longer than the wavelengths we can see. That's sort of the wavelength range. And that's important because it turns out that planets and a lot of other aspects of astronomy emit a lot of infrared light. Our Earth is a warm body. It emits infrared light. Our bodies are as well. And the nice thing about different wavelengths of light is that they can paint an entirely different picture compared to what our eyes see, right? This is the constellation Orion. I'm sure there's a lot of great amateur astronomers here. I'm sure there's many astronomers here who are far better than I am at sort of learning constellations. So we have Orion. We've seen it all so many times, right? Here's Orion with the belts. But if we look in the infrared, we see something entirely different. What we see is that this is sort of a stellar nursery. These are warm regions where new stars are being born today, new planetary systems. And so if we can look at our universe at a range of different wavelengths, we can learn a lot more about what's going on. And another thing about the infrared, right, is that it tells you something typically, at least about how warm something is. This is an astronomy professor somewhere holding his arm inside a plastic bag. Well, why would one do that? To sort of prove a point in that our eyes don't always see everything. If we have infrared eyes, we can actually see something entirely different. We can see the thermal heat radiation, wavelengths longer than we can see, coming off of this gentleman's arm. And so as we think about modern astronomy, we want to think about using different wavelengths of light. And there's lots of aspects of modern astronomy, including planets, and also studying very distant galaxies, where infrared light is really key to a full understanding of what's going on. And so this has been recognized for a while. This is sort of a wordy slide, but I want to get to why the James Webb Space Telescope exists at all. Every decade, a group of about 20 top astronomers in the country get together for what's called a decadal survey, and they set out the priorities for that next decade of astronomy. And so there was a decadal survey in 2000 that suggested that what we needed was eventually a replacement for the Hubble Space Telescope. And that was called the Next Generation Space Telescope, NGST. And wrote this report, Astronomy and Astrophysics in the New Millennium, from the year 2000. And the idea was by 2010, we would launch this amazing next generation space telescope. And we, of course, did launch that, but it did not launch in 2010. Did not even launch in 2020. When I was a young professor, I was anxiously waiting for this to happen because I knew it was going to be career changing for me, and eventually it did. It did in 2021. And so, of course, it got delayed. It was an extremely complex telescope. It's by far the most complex telescope ever devised. It happens to work in space. And so, of course, it had to be perfect, essentially, before it would be launched. And so that was, of course, why it got delayed, but it's really been transformational for a lot of us astronomical science over the past few years. And so this is not the real thing, but it's a display item in real size. And so you can see how large it really is. The main mirror here is 6.5 meters. That's about 20 feet across. It's a segmented mirror. Here it is in reference to the Hubble mirror. The Hubble mirror was actually the largest mirror that could fit aboard the space shuttle. It was the largest mirror that could fit aboard the space shuttle. And so the James Webb mirror needed to fold up to fit on a rocket, and then it has to unfold in space, which I'll talk about. So very large, much larger than the Hubble mirror. It also has these sort of sun shields I'm not going to talk a lot about, but they help keep the telescope cool. These sun shields actually point towards the sun so that all of the important telescope parts are in permanent shade. And so it actually launched Christmas 2021. At the time, I was in Minnesota visiting my family. And it launched on an Ariane 5 rocket from French Guiana. So the James Webb Space Telescope is mostly a NASA facility, but it also had a lot of contributions from the European Space Agency, ESA, and also a little bit from the Canadian Space Agency. And as part of the agreement, it launched from a European rocket from the European launch area, which happens to be this French territory, French Guiana, on the northern coast of South America. And so here's about a minute and a half launch. They were counting down backwards in French, if you could hear it.
Liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe.
I was watching this video again today, and I realized I know her. She works in our department.
Punching a hole through the clouds,
she's a European
20
astronomer,
seconds into
so
the
she
flight,
was there
good pitch
several years ago
program
as a
recorded.
European astronomer at the launch, and now she's in Santa Cruz. I had to watch the video twice, and I was like, I do know her. That's good.
The Ariane 5 rocket continues to fly uphill in nominal fashion.
And so we're going to switch from this movie to the next movie. This is sped up, but this is the real thing in space. This is sped up, and it's floating away, and it's shooting little rockets to get where it needs to be. I'll talk a little bit about where it got to. So it's unfolding solar panels. And this was happening, I forget it, like 3 or 4 in the morning on Christmas Day. And a lot of astronomers around the world woke up really early to try to watch it, and they were all excited. And I was like, you know, either it's going to work or it's not going to work. If I'm awake or asleep, it's not really going to matter. And so I really decided to get a good night's sleep. And so I was very pleasantly surprised in the morning when I woke up and everything was working great. So we orbit the sun, and then there's the moon's orbit. So we're 150 million kilometers away. And so it turns out, due to how gravity works, there's a few stable orbiting points around the sun. This is called the L2 Lagrange point. This is where the James Webb Space Telescope is today. It's another 1.5 million kilometers away from the Earth. And as we orbit the sun in 1 year, it stays at that point. It also orbits around the sun in 1 year. So it stays at a constant distance away from us. But of course, it turns because it has to stay in the shade. And so there are certain times of the year it can only look at various certain things, right? Because it always has to stay with the shades pointed towards the sun to keep the important electronic components cool. It's an infrared telescope, so you want it to stay very cold. If it warmed up, you would literally not be able to see anything because the telescope would see itself. It would see its own infrared radiation all the time. So you want to keep it incredibly cold, and that sunshade can do that. And so people have built, ingenious humans have built other infrared space telescopes over the years. So this is a view, I forget exactly, this is maybe a star forming region. This is WISE at 4.5 microns, so about 10 times longer than blue light. This is the Spitzer Space Telescope. When I was just getting started in astronomy, this was all the rage, really, really cool. And this is sort of a view of what we can see with the James Webb Space Telescope. These are, of course, not planets, these are stars, but it shows you the evolution of what we've been able to do. But what I'm not talking about today is images. So those were images that got better and better and better. What I'm talking about today is actually spectroscopy. And that is breaking light up into its component wavelengths to try to understand something about the physics and the chemistry of these exoplanets. In astronomy, we often take images to understand what people call the morphology, what things look like. But we also need spectroscopy to tell us about the composition of the things we are seeing. And those two are incredibly complementary in our modern view of understanding the universe. And so, of course, some materials absorb light at certain wavelengths, right? The sort of a classic example is that every element has its own fingerprint, right? Every human has a different fingerprint. Every element has its certain wavelengths. Hydrogen absorbs certain wavelengths. Oxygen absorbs certain different wavelengths. And we can also sometimes see some objects emitting light at particular wavelengths as well. And so these would be either absorption features, where we're seeing absorption, or emission lines. And so if we get a spectrum, we can learn about something's made of by looking at these particular wavelengths being absorbed or emitted. For atoms, they tend to absorb at very specific narrow lines. For molecules, which we see in planets, they absorb at a really wide range of different wavelengths, so it becomes a lot more complicated, but the idea is the same. This is just an example, Hubble. This is Eta Carinae. It's a star that's sort of having some problems. And this is a classic Hubble image. But we can learn something about what it's made of by breaking, this is the image is of course really cool, but by taking a spectrum and looking at particular emission lines, we can learn, let's say, maybe why that star is having trouble and what stage of its life it's in and what stage of its life it's about to leave. And so we can, by studying the composition, we can learn something about why that's happening. And that's sort of the idea of what we're trying to do with exoplanets, is learn about their atmospheric composition to learn about the physics and chemistry of those planets. And this is that particular spectrum broken up into different wavelengths. This is brightness versus wavelength to try to see different compounds coming from that star. So that spectrum really tells us something about the composition, about the temperature, about the pressure, maybe even about the dynamics, how fast things are going. With sound, we're used to the Doppler shift, right? If a train goes by with a certain pitch, we can learn about how fast that train is going. In astronomy, but with that Doppler shift of light, we can often learn how fast things are moving towards or away from us. And so what we're using the James Webb Space Telescope for, or JWST, is to learn about planets around other stars. And so in astronomy, we always have this sort of maybe tension, you might say. Some astronomers are trying to study the furthest things away from us, the first galaxies in the universe. There's other folks who are really, like myself, trying to figure out what's really nearby us, what's happening in the 10 or 20 light years just around us. These are the planets of our nearest stars, trying to figure out if they have planets, what those planets are like, and that's what the sort of thing I'm interested in. I'm not someone who finds the planets myself. I'm not someone who even points the Webb telescope. In my group, we're using physics and chemistry and making computer models to compare to the observations we're getting from Webb to piece that together to understand the composition of these planets. So we now know, I think this is actually past 6,000 now, planets around other stars. When I started college in 1995, that was when we found the first exoplanet around another star. When I started grad school in 1999, I think there was something like 7 or 8 planets known around other stars. And now we're up 6,000 and beyond. And so it's become a little more, it's become a lot easier to find planets. What's still incredibly challenging, though, is to learn what these planets are like. That's incredibly more challenging because it takes entirely different technology and much more data to try to piece together the atmospheres of these planets or to understand what they're like. And that's really what I've been trying to specialize in. And so I just want to mention how we typically find planets. 98% of planets around other stars, maybe 99, have been found by these 2 methods. So the first method, sort of the classic method, is this one in the lower right. When a planet orbits around a star, the planet's in blue, the star's in yellow, they actually orbit around their common center of mass. So if you imagine, they don't really make teeter-totters or seesaws anymore, right? But if you're on the seesaw, if you have 2 objects of the same mass, that center of mass, that fulcrum's right in the middle, right, going back and forth. But if you have if you're on your teeter-totter and one object weighs 1,000,000 times more than the other one, then that fulcrum is not going to be in the center. It's way over towards the heavy object. And one way of finding planets is to look for a tiny wobble of their star. And that tiny wobble of the star is because there's a planet orbiting around it. And you can build instruments to measure the speed of a star in meters per second. So that's a really that's really slow, right? I probably walk at a couple of meters per second. And we can watch a star wobble towards us and away from us, towards us and away from us, towards us and away from us. And that shifts the light blue to red, a Doppler shift. And I think almost 1,000 planets have been found this way. So you don't see the planet at all, you just see the star wobble around. Another method's the transit method. Here also, you don't actually see the planet, you see the planet's shadow. You see the planet pass directly in front of the star and block out a small amount of the parent star's light. From Earth, historically, we can do this. We can see Venus pass in front of the sun, we can see Mercury pass in front of the sun. But if we look out into the Milky Way galaxy, if we look at hundreds of thousands of stars, every once in a while you can see these tiny dimming events. And so if you're watching the brightness of a star over time, you can see a transit happen. And so the planets I'll be talking about today are planets that are relatively close into their star. Earth goes around the sun once per year. The planets I'll be talking about today are mostly orbiting around their star in 5 to 10 days. So they're much hotter, but they transit more often, so it makes them easier to find. And one of the amazing things we've learned over the past 20 years is that planets can be anywhere. We have found planets in like 8-hour orbits around their star, rocky planets that are probably just permanent magma lava worlds because they're permanently 3,000 degrees. We can find planets way further away from their star than Pluto is. Nature makes planets and puts them wherever it wants. And so one of the amazing things is that nature has ended up being a lot more creative than we are in thinking about what other planetary systems are like. And so the planets I'll be talking about today are actually exclusively these transiting ones that pass in front of their parent star. That allows us to measure the size of the planet. The bigger the planet, the more light gets blocked. The smaller the planet, the less light gets blocked. And then if you also follow up and do this measurement, the wobble measurement, that'll tell you the mass of the planet. The bigger the mass of the planet, the bigger the wobble. So we can measure the mass, the radius, the density. The density tells us something about what planets are made of. Our planet's a lot denser than Jupiter. But it doesn't tell you everything, and we'd like to learn more about the atmospheres. And so for exoplanet atmospheres, the things we're trying to do, the big themes of our field today, are to understand the physics and chemistry going on in those planets. And sometimes to think about how that knowledge of the physics and chemistry might tell us something about how the planets formed and how they might have evolved over time. Those are the big questions of the field. And so what I'll be talking about today are planets that pass in front of their parent star. That's called a transit. Towards the end, I'll also mention the idea of a planet that can pass behind its parent star. That's called a secondary eclipse or occultation. When the planet passes in front of its parent star, it blocks out a little bit of light. If you use your imagination, you could imagine if there's a thin atmosphere around the planet, there might be some of that star's light that might pass through that thin outer atmosphere. And maybe molecules in the atmosphere might absorb some of that light, some of that starlight, and we might be able to potentially detect that. When the planet goes behind the parent star, it's warm, it's glowing in the infrared. If we stare, we might see the planet disappear and then reappear. Now you wouldn't actually see it because it's so close in, it's just a big blob of light, but the total amount of light would go down when the planet's behind the star, and then it would pop back up when the planet reappears, if we're looking with our infrared eyes, and that's what the Webb telescope is doing. So we have transit and we have secondary eclipse. Mostly I'll be talking about the transit. So we're imagining light from the parent star passing through the thin outer atmosphere, and we're taking a spectrum of that light looking for molecules in the planet's atmosphere. And so this is just another artist's schematic. You could imagine there's our star, there's starlight, there's molecules, and we have this amazing telescope machine that can break that light up into its component colors, and we're looking for particular atoms and molecules that are absorbing light in the planet's atmosphere when it's passing in front of its parent star. And that thing on the telescope that breaks the light up is called a spectrometer or a spectrograph. That is the instrument on the telescope that breaks light up into its component wavelengths. And so here again, this is the electromagnetic spectrum. Visible light is just but a narrow wavelength. And as we go to slightly bluer wavelengths, we get to the ultraviolet. As we get to longer wavelengths, we get to the infrared, and that's where the James Webb Space Telescope is operating. This is a graph I grabbed from one of my scientific papers. It's way too detailed, but I just want to point out that these are different wavelengths of infrared light across from 1 micron to 10 microns, and different molecules like methane, hydrogen sulfide, water vapor, ammonia, monoxide, carbon dioxide, phosphine, all these molecules have absorption features. They're absorbing at all these different infrared wavelengths. So if we can observe across these wavelengths, these are the molecules, these are the molecular fingerprints we can potentially see in a planetary atmosphere. So for instance, at 3.3 microns, that's about 5 times longer in wavelength than we can see with our eyes. Methane, in blue here, methane is this weird sort of fist with a finger sticking up, and only methane does that at 3.3 microns. No other molecule absorbs like that at 3.3 microns, only methane does. And so if we're looking for these individual molecules, we can tell them apart, and potentially even find out how much is there. And so for the James Webb Space Telescope, the big science cases are studying the earliest universe, studying galaxy evolution, looking for young stars and the disks around them that form planets, and also trying to understand other worlds. And so this is a movie of what a transit sort of looks like. The planet orbits its parent star, and when it passes in front of the parent star, it blocks out a small amount of that parent star's light. Stars are much bigger than planets, of course, so the amount of starlight blocked out is small. So Jupiter is about 10 times smaller in radius than the sun. So Jupiter's cross-sectional area is 100th that of the sun. So if we could see Jupiter pass in front of the sun, it would block out 1% of the sun's light. If we could watch ourselves pass in front of the sun, we would block out 0.01% of the sun's light. This is a very small effect. It's drawn here to be sort of bigger than it really is, so you can see it. And so this is real data from the Webb Space Telescope. This is the brightness over time. This particular planet called, I believe it's called WASP 96. It's the 96th planet from the WASP survey. Some planets have really boring names. This is 98%, so it blocks out about 2% of its parent star's light. So this is the normal brightness. The planet blocks out 2%, and then it goes back to normal. If you look in detail at 3 different colors, 3 microns, 4.3 microns, and 4.7 microns, it turns out that you can clearly see that at 4.3 microns in green, clearly let's say, the planet's blocking more of the parent star's light than it is at this red wavelength. The transit is deeper, it's blocking more light. That's because the planet's atmosphere is actually absorbing more of the star's light at 4.3 microns. And at 4.7 microns, that atmosphere is more transparent. It's letting that light through. And so this is the sort of, these are the tea leaves we're trying to read by looking at how much light gets blocked out as a function of wavelengths, to learn about what molecules are absorbing in the planet's atmosphere. And so it turns out this is the first molecule detected in an exoplanet atmosphere with Webb, and I'll tell you the fun story behind this in a minute. This is 2% of the parent star's light. This is WASP 39b, the 39th planet in the WASP survey. And if we look at 4.3 microns that I mentioned, boy, there's a lot of extra absorption there. It turns out that carbon dioxide, CO2, absorbs at 4.3 microns. And we see that a really strong extra absorption. This is more of the star's light being absorbed at that particular wavelength. This is the amount of light blocked. So it's highest at this particular wavelength. And so this was observed in 2022, summer 2022. There was a big program. This is the Webb telescope going into, I think this was after they were testing it. They were going to, of course, put it on the rocket and bring it down to South America. You can see humans for scale. I was part of a really large collaboration led by my colleague, Natalie Battaglia, just down the hall from me, and some other folks. 300 collaborators around the world. The idea was to use 80 hours of JWST time to understand how the telescope was performing by looking at a few different exoplanets. There was another collaboration looking at stars. There's another one looking at galaxies. Ours was about looking at a small number of exoplanets. So it's called the Early Release Science Program. So we were the first people in the world to see this data come down. Whoops. And so in Santa Cruz, in July 2022, we were all at the Other Worlds laboratory. There was a group of about 80 of us just waiting and waiting for the data to come down. And then it came down, and a former UC Santa Cruz undergrad, Zafar Rustamkalov, who is now getting his PhD at Johns Hopkins, he defends in a month, he was working with his advisor and made this first exoplanet spectrum. As a second-year grad student. And this is the amount of light blocked versus wavelength. This is someone's photo of this laptop. And you can clearly see at 4.3 microns, there's this really big absorption feature. Maybe it was like, oh my God, this was huge. And it was like, oh, this is CO2. There's nothing else that absorbs at 4.3 microns that clearly. This is actually due to water vapor absorption. This other big feature there, that's water vapor. This was all a big mess that we had to figure out later. But this was CO2 absorption. And so this was, of course, really exciting. That's Zafar right there. He made the spectrum. That's my colleague Natalie. That's Dave. He's Zafar's advisor. Sarah and Mike, these are all colleagues and friends of mine. I happened to have COVID that week, and so I was home, sick, following along on my computer. Wasn't nearly as exciting, but for the folks there, it was tremendously exciting the first time we had that spectrum. So that was July 15th, 2022. And so we had known about this planet before, but I want to show you the difference between Spitzer Space Telescope data and James Webb Space Telescope data. This is the amount of light blocked. Instead of in percent, it's in parts per million, but it's the same idea. This is 3 to 5 microns. Spitzer had given us these 2 blue points. Well, what can you learn from 2 blue points? It's hard to say. But with a real spectrum, we could know this slant here is due only to water vapor that does that, and this big point up here is due only to carbon dioxide. So these are the 2 molecules we saw right away. This is from an instrument called NIRSPEC, the Near Infrared Spectrograph, aboard the James Webb Space Telescope. This is the complete spectrum. We published a really short paper in Nature confirming that we had detected this atmosphere. And so this is due to, these are 4 different groups who analyzed the same data. Thankfully, they all got basically the same spectrum, which is good. It's the same data. They should get pretty much the same thing. And this is the big carbon dioxide feature. And we were looking through the spectrum, and it was sort of like, okay, well, what's that thing? It's like, well, I don't know. I didn't know. Some other people didn't know. And so we went through and we looked at different, again, this is the same spectrum. These are different molecules. So CO2 absorbs very strongly at 4.3 microns. And we have things like methane and water, carbon dioxide. Nothing has this bump here at 4.0 microns. That bump just wasn't there. And so what is that? And so we have this big collaboration of like 300 people all over the world, and there's all sorts of databases around the world for different molecules and atoms that absorb at different wavelengths. And people were racing to try to plot up different molecules from these databases to find, well, what in the world absorbs at 4.0 microns? And so we're thinking about it, and I don't know if folks use Slack. So Slack is a communication tool. It's a lot like Discord, or as my kids call it, it's like Discord but for work, because they use Discord just for fun, right? So it's a way to communicate around the world, right? And so there's a channel that we had called Wild Theory Speculation. What is this thing at 4.0 microns? And it turned out that we figured it out, and it's a molecule SO2, sulfur dioxide. And this is only made in planetary atmospheres via photochemistry, when ultraviolet light breaks apart existing molecules and they reform into something else. And so Shami Sai is a young scientist who's at UC Riverside now. And what he figured out is that this is actually made only at a certain level in the atmosphere. This is pressure. This is down deeper in the atmosphere. This is higher up in the atmosphere. And this particular planet, it's sort of like Saturn. It's a warm planet. It's intermediate between Saturn and Jupiter's mass. It's a gas giant, but it's more like 1,000 degrees. It's in a very close-in orbit. And it's so close in that ultraviolet light is constantly breaking apart molecules in the planet's atmosphere. And so what happens is that ultraviolet light breaks apart water vapor. And the water vapor fragments attack other molecules in the atmosphere. And it attacks hydrogen sulfide, which would be the stable molecule in the dark. But it's not in the dark. And then it gets broken apart. And it makes this layer of SO2. This is the amount of that molecule in the atmosphere. And it makes this fun little bump right at 4.0 microns. And we can actually figure out the abundance, Vulcan's the name of a computer code, of the amount of that SO2 that fits the exact amount of that bump. It's about 1 part in a million. It's not a very abundant molecule, 1 part in a million. And this is a schematic of ultraviolet light hitting water vapor, breaking it apart into hydrogen and OH. Those OHs are really reactive. They're going around and they're wreaking havoc in the atmosphere. The hydrogen sulfide molecule was happy in the dark, but then it ends up through a chain reaction getting broken apart into sulfur. OH finds it, and it ends up making SO2. So this is sort of the reaction pathway from start, here's the start, and the start to finish. Hydrogen's in white, oxygen's in red, sulfur is in yellow. You make SO2 in the end. And we've since seen this molecule in several other close-in, warm gas giant planets. So it seems to be a ubiquitous thing that's happening. This is the first time anybody had ever seen it. So I want to move on from the WASP-39 sulfur story to talk about some of the other planets we've been observing. I'm part of a group called the Manatee Program. We have this fun logo. We also have stickers, because everyone has stickers these days. This is a very tortured acronym, something about mid-infrared assessments of transiting exoplanets. It's very long and tortured, but we have a cool logo, so that's really the important thing. And so what we're looking at are relatively warm planets, but a little bit cooler than some of the ones I talked about so far. So these close-in gas giants are often called hot Jupiters. They're gas giants like Jupiter, but really close into their star, maybe like 2,000 or 1,500 degrees. The Manatee collaboration is looking at relatively cooler planets to look how the chemistry changes when you get to cooler objects. A planet like Jupiter is incredibly cold, much colder than the Earth. And so we'd like to understand the continuum from hot planets to cold planets, because this is the first time we can do this with this amazing space telescope. So this is a paper that we published last year looking for methane. And indeed, this was the first time we had found methane in a planet around another star. And it turned out we were able to see it both in transmission when the planet passes in front of its star, and in emission when the planet passes behind its parent star. We can see this 3.3 micron weird finger. I'm not going to hold up my middle finger, but that's sometimes what people call it. It has this interesting little feature here at 3.3 microns where it sort of peaks up in the middle. And we can see that methane absorption. The real data is in black. It's really pretty noisy. Our computer model is in the different colors. And the green model includes methane, and the orange model doesn't have any methane. And you can sort of see we fit the data a lot better there. That's the transmission when the planet passes in front of its star. If we instead look for that when the planet passes behind its parent star, we again see this excess absorption due to methane at 3.3 microns. This planet's relatively cold. It's around 900 degrees, which is cold for a lot of the objects we've been studying. It's on the continuum towards finding objects like Jupiter. This was another new molecule that we were seeing for the first time in a transiting planet atmosphere. My favorite actually is this one. So we made the cover of Nature, which is a pretty big deal. This is a planet called WASP 107, the 107th planet found by the WASP survey. But it's actually a really interesting object in that it's in an eccentric orbit around its star. In our solar system, almost all of our orbits are quite close to circular. But if you're close into your star and you're not circular, that squeezes the planet. Tides change a planet's shape. Earth changes shape because the moon orbits around us, right? We have tides. And that actually squeezes the Earth's shape. WASP 107's really close in, and it's on an eccentric orbit, so that squeezing changes over time. When it's close to its star, it gets squeezed a little bit into like a football shape. That's called being prolate, like a football or rugby shape. When you're further from the star, you go back to more of a circular shape. So you get squeezed, unsqueezed, squeezed, unsqueezed. That actually leads to heat being dissipated in the planet when it gets squeezed over and over again. What it does is it heats up the interior, and it makes a planet that we think otherwise should be about as big as Uranus or Neptune, which is about 4 or 5 times the radius of the Earth. It gets squeezed up to a radius twice as big, or a volume 8 times as big. So we decided to call it a popcorn planet. It's like a kernel of popcorn getting puffed up due to heat. It's puffed up. And so that heating puffs up the size of the planet. It's twice as big as it should be. And that heating actually changes the chemistry of the entire atmosphere. The deep interior is hot, the atmosphere is hot, and that hot atmosphere changes the molecules that we would otherwise see. So this popcorn planet, we measured carbon monoxide, carbon dioxide, and methane, all in the atmosphere of this puffy popcorn world. This planet's so puffy, actually, its bulk density is actually similar to styrofoam. Its mass and radius, you can measure it, it's less dense than styrofoam. So people talk about Saturn being not very dense. Saturn can float in a tub of water. That's the classic thing they say about Saturn, it's less dense than water. This planet's 7 times less dense than Saturn. It's a big puffball. And this is actually the real spectrum from the Real Science paper. It's about 720 degrees in Kelvin. I'm forgetting that in Fahrenheit. Maybe I'll figure it out later. When it passes in front of its parent star, it blocks out around 2% of the parent star's light, but then it absorbs extra at certain wavelengths. And so this is due to water vapor. This is our little bump of sulfur dioxide at 4 microns. This is carbon dioxide at 4.3 microns. This is carbon monoxide at 4.5 microns. All these different molecules have their fingerprints, right? This is a brown CO2, we can see it right there. This is water in light blue here. We can see it right there. So all these molecules we can see in this planet's atmosphere. So we can take a molecular inventory of what molecules are in it. And it turns out we think its composition is sort of like Saturn's. It has a lot of heavier stuff, but if you heat it up Saturn by cranking up its temperature. One other cool thing we've been doing with the Webb's telescope is looking for clouds. On Earth, clouds are made of one thing, water vapor, water. If we go to Jupiter, we actually have clouds made of a different thing. We have clouds made of ammonia, ice crystals. If you have a planet that's 2,000 degrees, it's way too hot to have ammonia clouds or water clouds, but one of the things you can have are rock dust clouds, because it's 2,000 degrees. And rock dust that's the thing that's turning from a gas to little particulates. This is another planet it's another WASP planet. And this is the amount of light this is again, infrared wavelengths, and this is how much light is being blocked out. In the laboratory on Earth, we can measure different kinds of rocks, quartz rocks, forsterite, enstatite, any sort of rock you could pick up on the ground. You can make a dust out of it, and you can look at what wavelengths of light it absorbs at. And almost all rocks actually absorb a lot of light between 8 and 10 microns, maybe like 20 times longer wavelengths than you can see. Everywhere in the universe, we can see dusty rock dust absorbs around 10 microns. And so this is a pretty subtle, but if you look over here around 8 to 9 microns, what these clever scientists note is that there's an extra absorption here. The data is in black. And what they found is that this is quartz, SiO2. So this is the extra bump here at around 8 to 10 microns that we think is a quartz cloud in this 2,500 degree planet. And so everywhere we look, we see surprising things, but they make sense based on our understanding of physics and chemistry. If you're over 2,000 degrees, you're not gonna have water clouds. You're gonna have maybe iron rain droplets, rock dust clouds, and that's the thing we can see around these hot planets. So we're building an exoplanet library of the gas giants. And in a minute, I'll start talking for the last 10 minutes or so about smaller planets. But this is an artist's rendering of a bunch of different multicolored worlds. This is all the artist's conception. But these are the planets, these are the molecules we're seeing. Carbon dioxide, sulfur dioxide, methane, ammonia, carbon monoxide. So about 50 planets have had spectra measured with the James Webb Space Telescope. I covered what I think are really cool, 5 or 6 of them. But over the next few years, we'll move from 50 to several hundred. So we're observing something like 50 or 60 planets per year, building up a library of the molecules we're finding in all these exoplanet atmospheres. And so we want to do that for hot, warm, and cold planets to see how that atmospheric chemistry changes. And so in my last sort of 10 minutes or so, I want to talk about some of the initial reconnaissance we're doing for small planets around other stars. Everything I mentioned today was sort of Neptune to Jupiter size objects, and those are hydrogen-helium dominated atmospheres. Hydrogen-helium dominated atmospheres. Our atmosphere is, of course, nitrogen-oxygen. Venus's atmosphere is carbon dioxide. Very little hydrogen or helium. And so we want to find planetary systems where we can try to use the Webb telescope to understand atmospheres of small planets as well. And so the way to do that is to find small stars, right? If we're seeing a planet pass in front of a star, if the star's big, it's going to block out very little of the star's light. If the star is tiny, it'll block out more of the light. And about 7 years ago now, there was a system found called TRAPPIST-1. TRAPPIST-1 is a really faint, very feeble star. It's barely a star. It's 1,000th as bright as the sun. 1,000th as bright as the sun. It's only about 80 times the mass of Jupiter, and it's barely bigger than Jupiter. It's a small, faint star. The amazing thing about TRAPPIST-1, though, is it has 7 planets orbiting around it. This is some of the data. This is the brightness of the star versus time in days in 2016, so 9 years ago. And if you look over time, what you see is over the course of 3 weeks, what you see is that the star's brightness isn't always the same. You can sometimes see there's things happening. The star dims over and over and over again. And the star's dimming over and over and over again because there's planets orbiting around it. This magenta dot is a planet that orbits every 1.5 days. It blocks out some of the parent star's light. In green is the planet that blocks out lights every 10 or 12 days. And it turns out, amazingly, there's 7 Earth-sized exoplanets around this small star. 7, all really tightly packed in. This is the TRAPPIST-1 system. This is an artist's idea of what they might look like. We don't know this yet. But the size of the system is incredibly tiny. So this is to scale. This is where Mercury, Venus, Earth, and Mars orbit. Earth is in what we call the Goldilocks zone, or the habitable zone. It's not too hot, not too cold. It's just right? That's where we live. And the size of the TRAPPIST-1 planetary system to scale is in here. You have to blow it up a factor of 25 to see this in here. It's a tiny star. Okay, now it's not to scale anymore. The planets are not actually bigger than the star. But these are all sort of 0.7 to 1.2 times the size of the Earth. Some are a little smaller, some are a little bigger, but they're all around the same size as the Earth. This parent star is really faint, so if you're really close in like a 5-day orbit, it might actually be a really nice place to be. It could be actually quite toasty warm, but not too hot. So this Goldilocks zone, this habitable zone around this faint star actually sits here. So planets D, E, and F might actually be in the potentially habitable zone. And so the question is, well, can we use the James Webb Space Telescope to look for atmospheres around these planets? We can. Okay, sorry. Yeah, we're looking for carbon dioxide or something. I forgot this click-through release. So I want to tell you just about the story of the first time we tried to do this. People have followed up to look at other planets. We have not detected any atmospheres yet for these particular planets. The first one we looked at was planet B. This is the closest in object. B is the one closest in, the hottest object. And I have to click through these again, I apologize. So B is in the planet, it's in a 1.5 day orbit, but the star is really faint, so the planet's only around 600 degrees. That's not so bad, it's not as hot as Venus. And this is the brightness versus time. And this is time in hours, 1 hour, 2 hour, 3 hour. And this little dip here is when the planet passes behind the parent star. And we see the thermal infrared heat radiation disappear and then reappear. The planet passes behind the star, it's gone for about 45 minutes, and then it pops back out again. And by looking at how much light is lost, we can take the temperature of the day side of the planet. We can tell how hot the planet is. If it's very cold, we would see less starlight getting blocked, or less planet light getting blocked. If it's really hot, we would see more getting blocked. And so we can take a temperature, and we measured something that's around 430 Kelvin, sorry, 420 Fahrenheit. So the top axis is Fahrenheit, the bottom axis is Kelvin. I use Kelvin all the time, but of course I'm an astronomer. So it's 430 Fahrenheit or so pretty hot. And what that actually told us was that this planet does not have an atmosphere. It turns out that bare rock is really dark. It doesn't seem that way, but in reality, bare rock absorbs energy really well and it heats up. Atmospheres are really good at scattering light to space. So if we'd measured a cool temperature, that would indirectly tell us that it had an atmosphere that was scattering light back to space, so the planet never got super warm. What we measured was sort of the maximum possible temperature. We measured the maximum possible temperature because we think there's no atmosphere and that bare rock just absorbs all the parent star's light and radiates that infrared light back to space. And so planet B, no evidence for an atmosphere. People have also looked at planets C and D. So far, no evidence for an atmosphere. And so one of the reasons why we think that is that this small star, although it's very faint today, we think it probably was actually not always so faint, and that probably helped drive off the atmosphere when the planets were young. It turns out this is the brightness versus time. The sun is in black here, and the sun actually maintains a fairly constant brightness over millions to billions of years, fairly constant. It turns out these small faint stars that are really faint today start their lives out being many, maybe 100 times brighter. So the planet today might be in a fairly nice, relatively cool orbit, but when the planet was forming, that star was probably 100 or maybe even 1,000 times brighter. And so we think these small stars might drive the atmospheres away from the small planets. And that's one of the things we're trying to test with the James Webb Space Telescope today and over the next 10 years. Do these small planets actually have atmospheres at all? So it's a very nice complement. For the gas giants, they all have atmospheres. We'd like to know what they're made of. For the small planets, we'd like to even understand if the small planets have atmospheres at all. And then if they do, then we can try to figure out what those atmospheres are made of. I think this might be my last slide. So the takeaway messages as you go home, drive home tonight. Up until now, this is the 4th year of the James Webb Space Telescope. We've observed about 200 exoplanets by the end of cycle 4. Not all that data has been published yet, but it will be. And so we'll learn in the first 4 years about 200 planets, what their atmospheres are like, or if they have atmospheres. That's in the first 4 years. We're hoping the Webb lifetime might last for perhaps up to 20 years. The launch actually went basically perfectly. It has a lot of propellant to keep it in its stable orbit. And so the telescope things will break over time, but we're hopeful it could last 10 or 20 years, which to me is really, really amazing. We can keep adding to this exoplanet catalog as time goes on. It allows us to do 2 things. For the giant planets, things that are Neptune, Saturn, Jupiter class, we can really look for trends over the course of hundreds of planets. We live in a solar system that has 4 giant planets and 4 rocky planets. All of our lessons learned about what atmospheres are made of for giant planets comes from a sample size of 4. In astronomy, that is bonkers. We would know nothing about stars or galaxies if we only had a sample size of 4. And so in the modern era, we have spectra of millions of stars, millions of galaxies. So exoplanets lagging behind by 50 or 100 years. So in my field, going from a sample size of 4 to, let's say, 400 or 1,000, that's amazing to thinking about the lessons we're going to learn. For the rocky planets, I think over those 20 years, we'll be able to do a reconnaissance for maybe about 10 or 20 planets, asking the question, do they have atmospheres or not? If none of them do, it's a big bummer, but it's an important lesson to be learned. And so, but if we do find a small subset that we think have atmospheres, then we can put a lot more Webb telescope time to those particular lucky few to then try to understand what those atmospheres are like. And that's sort of the plan over the next sort of 3 to 5 years with Webb, is to do more reconnaissance of 10 to 20 to figure out if they have atmospheres or not. And so that's where the field is going. I hope I gave you sort of a good taste of what we're doing. It's really great to be here, and I'm happy to take any questions.
Hello. In one of your early charts, you showed a list of names of molecules and wiggly lines about the spectrographic characteristics.
Yeah.
Now, the top left molecule was H2, hydrogen.
Yeah.
But after H2, it said CIA. What is CIA?
Yeah, sorry. It's nothing nefarious. It's collision-induced absorption, CIA. So hydrogen, H2, like nitrogen, N2, is mostly transparent. You know, Earth's atmosphere is mostly transparent, right? The H2 molecule is mostly transparent. But it turns out that when the H2 molecules collide with each other, they perturb each other's electron clouds, and that allows them to absorb infrared light that they wouldn't otherwise absorb. And so the collision-induced absorption is a thing we can see in planetary atmospheres. We can see it in Jupiter's atmosphere, for instance. That's what the CIA stands for.
Now, speaking of Jupiter's atmosphere, sulfur dioxide, is it created in the atmospheres of Jupiter and Saturn?
It seems to not be, and that's the main reason why, is that Jupiter's atmosphere does have this H2S that could be broken up, but Jupiter's atmosphere has almost no water vapor. And so you need the water vapor to be broken apart by the ultraviolet light, and the water vapor fragments attack that sulfur molecule. In Jupiter's atmosphere, it's so cold that any water is stuck in a cloud way below the visible atmosphere. So Jupiter's atmosphere is dry, so that reaction doesn't happen. Great question.
Thank you for your talk tonight.
Sure.
With the JWST, how long of an observation do you need to get an accurate spectra of these planets?
Yeah, great question. So for the bigger planets, the gas giants, the hot Jupiters, we can observe just a single transit. And so that probably takes it blocks out the star's light for about 3 hours, and so you want sort of an hour or two on either side of that. So typically 5 to 6 hours is for a gas giant. For that small TRAPPIST-1 planet, that little guy, we observed that 5 times repeatedly to build up better signal. So typically for the gas giant planets, we observe them once or twice. For the smaller planets, typically sort of twice to maybe even 10 times. And then if in the end for a small planet, if we see a signal that maybe it really would have an atmosphere, there's been discussion about, maybe in a few years' time, trying to observe, maybe 30 or 40 transits, because the science question might be big enough. So it really varies by the object, but mostly just maybe 5 hours. Yep.
I just saw a recent publication where the Webb Space Telescope took some data of a very strange object called SIMP 0136, which could be a brown dwarf. Mm-hmm. And I'm wondering, how do you find such a thing? What do you understand about such things? What temperature are they? And it measured the rotation of this object and was able to determine the composition of the atmosphere. Could you talk something about that?
Sure, yeah. So a brown dwarf is sort of intermediate between a gas giant planet like Jupiter and a star. So when stars are formed, we think stars form out of these big clouds of gas. Those are called giant molecular clouds. And different regions of that cloud collapse under gravity, and that's how we think stars are formed. But stars can be formed over a whole range of masses. And the smallest objects that form like stars might be so low in mass, maybe 10, 20, 30 Jupiter masses, that when they contract and heat up, they don't get hot enough for fusion. So they just keep cooling off. One of the things we've learned over the past 20 years is that in addition to studying exoplanets, we've learned that brown dwarfs are about as numerous as real stars. So for every star you see in the sky, there is also a brown dwarf that you can't see. They're very cool. They only put out infrared light. But with an infrared space telescope, if you look up in the sky, they pop, you can see them. So I mentioned that previous space telescope called WISE. That was when I had those 3 panels on the front. So the left panel was an all-sky survey in the infrared, and that found thousands of brown dwarfs. So they are, the smallest ones cool off almost as cold as Jupiter. The biggest ones that are maybe 70 times the mass of Jupiter, they cool off to maybe 2,000 degrees, so still much cooler than a star. And so the nice thing about them actually is that they don't have a parent star. The trouble with planets is that they have this really bright parent star we got to worry about. A brown dwarf, no parent star. So if you find one, within 15 minutes, you can usually get a really nice spectrum of the atmosphere. So for brown dwarfs, they actually test our understanding of planetary atmospheres because they actually have temperatures very similar to planets. They're just cooling off over time. So all those same molecules I mentioned, almost all of those we see in brown dwarfs. We don't see that sulfur dioxide molecule because that's only formed via photochemistry, so you need the parent star's ultraviolet light. Those other molecules, we see them. And then the nice thing about brown dwarfs is that you can get a really, really nice data. So if you keep staring at them over the course of 5 or 10 hours, you can actually see them be variable over time. They're not constant in their brightness. And we think that's because they're rapidly rotating like Jupiter is. And so the amount of infrared light we see changes over time because we think they have hot spots and cold spots. They have these rock dust clouds, can be patchy, so some parts might have more rock dust clouds or less rock dust clouds. And so brown dwarfs are really interesting, just sort of learning about planetary physics in the absence of a star. And they're very numerous, so we can study them in a lot of detail.
Dr. Fortney, your energy for this work is really palpable, and thank you so much for the talk today.
Thanks.
I'm curious because you called out since 1995, going from 50 exoplanets to now whatever, 1,000-ish.
Yeah.
Not once did you mention AI, and I am so tempted to, ask you, do y'all use AI at all in terms of discovery, and if so, how?
Yeah, people have started to do that in the last few years. There's definitely been a few successes of new planets found in old data. So I mentioned the Kepler Space Telescope that stared in one patch of the sky for 3.5 years. It monitored the brightness of about 150,000 stars. That's all it did. And it found over 3,000 planets. And there was computer software written to monitor this brightness to look for these transits. And so what folks have done, and so that was that was like 2010, in the ancient times, 15 years ago. And so and there's a new space telescope called TESS, the Transiting Exoplanet Survey Satellite. That's an all-sky survey of just the bright stars looking for transits. And so folks have started to do, really it's machine learning, it's teaching, it's training them to look for transits. And so there's definitely been a few successes, but I think that's still sort of in its infancy. I think that area is really, really big in other areas of astronomy, where you might have thousands or millions of images of galaxies, and you need to classify what you're seeing. And so there's definitely a lot of successes outside of exoplanets where things have been robustly done for a long time. But I'd say in planets, we're just sort of getting started, I would say.
Thank you.
Yeah.
Hello, Professor. Thanks for the talk tonight.
Sure.
I was wondering if it's possible to look at the age of exoplanets or brown dwarfs by looking at the spectra. Say, like if you have like isotopic ratios that you can detect, different like molecular modes that would only happen with certain isotopes. Because that's really interesting for me for like when planets started forming in the universe. So just any information on that would be great.
Yeah, that's a great question, right? So on Earth, we know our system is 4.56 billion years old. I mean, we know that from radioactive dating, right? For exoplanets, we're often, I wouldn't say we're flying blind, but it's really, really challenging. I think for 5 planets, people have been able to detect some isotopic ratios. You can't do that with Webb. You can do that with certain ground-based telescopes. And so people have measured the deuterium to hydrogen ratio in one brown dwarf. People have measured different carbon, about heavy and light carbon, in maybe 3 of the hot Jupiters. No one's been able to tie that to age or anything yet. Mostly what we do is we assume that the planets are probably formed the same time as their stars, to within, and so almost all these systems are quite old. They're sort of billions of years old. But typically it's very hard for us to say, well, is this system 3 billion years or 7 billion years? It's often very difficult to say. So that's age dating of planets and stars is sort of one of the last great challenges, because it's really difficult. And so, some isotopic abundances have been measured, but we haven't been able to connect that to age.
Thank you.
Great question.
Well, thank you, Dr. Fortney, for a very interesting and informative discussion.
Thanks.
Does the Webb have the ability to detect artificial molecules such as carbon tetrachloride or trichloroethylene? And if such molecules were detected, what would be the implication?
Yeah, it certainly can observe from around 1 micron to about 15 microns in terms of good spectra. And so there are human-made molecules on Earth that do absorb at those wavelengths. The challenging thing is a lot of these human-made molecules are sort of at the part per 10 billion level. And so we can measure them on Earth because we live here, but to an outside observer, they wouldn't necessarily be apparent. And so while we have the wavelength capability, I wouldn't say we have the sensitivity to detect human, inorganic, whatever you want to call it, right? Manufactured molecules. If we did, of course, that would be tremendously exciting. So it's very complementary to what people call SETI. People are looking for, it is SETI, right? It's techno-signatures, looking for technology. And so one way of looking for technology is looking for, radio waves from planets. Another way of looking for technology is looking for things that would have to be made via technology. And so that's a growing area of astronomy, but I think Webb is not going to be able to do that. Great question, though.
Thank you.
So we'll have 4 more questions before people.
Okay, great.
So I can ask 4 questions? Okay. This might just seem very simple, but I've just wondered about it. I hear tell about planets that orbit their stars in hours.
Yeah.
And it seems to me like, wouldn't they be within the photosphere? And if so, would they only be detectable by the Doppler method and not by the, whatever that is, the light
Transit
dimming method?
Uh-huh.
So that's,
Yeah. There is a distance inside of which no one has ever found a planet. I think that's like a 6-hour orbit, which is sort of crazy to think about. But as you go to 20-hour, 30-hour orbits, they're not very common, but you definitely see planets. And so it's sort of, to some degree, yes, it is sort of in the outermost layers of the star, but it's the density of the star is very, very low. And so they're not feeling much drag, so they're not being dragged into their star. And although it's quite hot, it's not necessarily hot enough to obliterate the planets. So we can see gas giant planets in sort of 20-hour orbits. Inside of that, they don't seem to be stable. And we can see rocky planets down, very rarely, down to 6 to 8-hour orbits. Some of those rocky planets, we actually can see a rock dust cloud following them like a comet. So that's been seen. So there are limits for how close in the planets can be.
all right, thank you very much.
Sure.
A really stimulating talk. I would love to zero in on maybe biosignatures.
Yeah,
and,
sure.
You know, the question that a lot of atmospheric research is, any signs of life out there?
Yeah.
And specifically, I'd love to bring it into the solar system for a minute with phosphine, Venus.
Yeah.
Could you talk about the scientific discussion around whether it's actually there, and if we can't agree or can agree on the phosphines in Venus, if we're going to agree on low concentration gases in an exoplanet 100 light years away. Could you talk a little bit about that? Because I'd love to find a little bit more about signs of life.
Yeah, no, it's a great question. So the two things that are in the solar system that are relevant to this discussion is maybe 15 years ago, people used ground-based telescopes to find methane in the atmosphere of Mars. And that was a big story, 20, methane in Mars's atmosphere. And then people changed the instrumentation on Mars landers and Mars orbiting spacecraft to better map the amount of methane in Mars's atmosphere. Because it was amazing, how could there be methane there? And none of these objects since then have found any methane in Mars's atmosphere. And it turned out the original discovery was made by scientists at NASA Goddard Space Flight Center in DC, and some scientists at NASA Ames in Mountain View went back through everything themselves, and they actually found that the signature of methane in Mars's atmosphere was actually due to a signature of methane in Earth's atmosphere, where one of the hydrogens was heavy hydrogen, deuterium, and that shifts the lines very slightly. And that was not corrected for in Earth's atmosphere. So what these folks had been detecting was a variation in Earth's methane. And when you go to Mars, there's rovers, there's spacecraft looking down. They could see any methane that would even be 1,000 times less abundant. And it doesn't seem to be there. So that's a great lesson. The phosphine, this was detected via a radio telescope. I guess it was maybe 3 or 4 years ago now. A variety of other groups looked at that same data set. And some folks said, oh, well, we see this phosphine absorption line, pH 3. Other groups said, well, yeah, if you treat the data this way, sure, but if you do it this other way, we don't see it. Phosphine, pH 3 on Earth is what people call a biosignature gas. It's only created by biology. Methane can or can't be, it doesn't have to be biology. And so I think I would say almost all professional astronomers now don't think there's a great sign for phosphine in the atmosphere of Venus. Phosphine also absorbs in the infrared, not at radio wavelengths, and we have really good infrared data. It doesn't seem to be there. So that to me those are both great lessons that, NASA has plans to build this thing called the Habitable Worlds Observatory, which I really hope it does in the 2040s, to look at the atmospheres of potentially Earth-like planets around sun-like stars in reflected light. And Earth is 10 billion times fainter than the sun in reflected light. But in the laboratory, we can see things 10 billion times fainter, so it's only an engineering problem to get it up on the telescope. And I think that it is definitely a solvable problem, but it does definitely teach us that the exciting science is always on the hairy edge, and sometimes the things on the hairy edge turn out to be real, and sometimes they don't. And we've seen that many times over, and I think that's a thing that we have to be wary about when we're getting these initial reconnaissance of other planets.
Thank you.
You're welcome.
Hi. So I wanted to ask, on the rock dust clouds that are on the gas giants, the gas giant exoplanets, how do they form?
Yeah, that's a great question. I'll talk about iron and I'll talk about rock dust, because they're both hot, right? So we think that iron clouds form in the same way that water clouds form on Earth. Water clouds form because there's only so much water vapor that can be mixed into the atmosphere. When the atmosphere gets cold, then not as much water vapor can be mixed in, and the extra water vapor forms little droplets, and that's what clouds are. If you go up in the atmosphere, it gets colder and colder and colder, and eventually you can't mix in water vapor anymore, and you form a cloud. In Santa Cruz, right, we have fog, that's clouds at the surface, right? And we think hot planets, when they have too much iron vapor in the atmosphere, turns out stars have a lot of iron vapor, and when that gets cool enough, you form little iron droplets. The rock dust, we think, is actually something totally different. We think it's actually a chemical reaction. If you have silicon vapor and you have magnesium vapor, when that gets cool enough, and there's also water vapor around, cool enough being like 2,000 degrees, you form a chemical reaction and you make that quartz or silicate dust just from the chemistry because it gets cooler. And those rock dust clouds, which seem sort of crazy, in these brown dwarfs that gentleman mentioned, we've seen these rock dust clouds in hundreds of objects. So we know for sure, although the data I showed you is like, well, what is that? Is that really what I said it is? We really can see this rock dust clouds in all sorts of these cool brown dwarfs.
Thank you.
You're welcome.
Thank you for an amazing tour, and thank you for your fortitude with the questions. Ladies and gentlemen, we will see you again in May for discussions of Pluto. Thank you all for coming, and drive safely.